Welcome back. In this video, the third in our series about diffusion image filtering, we're going to talk about explicit approximation methods for the heat equation. So let's first do a very quick recap of what we studied in the first two videos. So in the first two videos, we saw that to solve the heat equation, what we are actually doing is we are picking an initial signal, alright? This one that we studied, something like this. And all that we're doing to solve this equation is perform a convolution with a Gaussian, right? Okay, so now and then this method works, okay, and then we saw that we could do this operation by means of the FFT, the fast Fourier transform, and the FFT is actually pretty fast. It runs in around O n log n complexity, right? And this is already pretty good and gives us the exact solution. So you might ask, why do we even want to approximate solutions then if we can solve the exact problem so well? Well, the thing is, usually when you're working on a practical problem, you don't really solve exactly the heat equation. You solve an equation that has like some nonlinear terms where the diffusion is only one part of it. For example, we're trying to solve a reaction diffusion system where you would have where this function here would be the concentration of some chemical, and then there are some nonlinear terms to control the concentration of chemicals, or you have some viscosity that is nonlinear with respect to diffusion, and these Fourier methods, they will not work if the equation is nonlinear, right? So we're going to study approximation methods because when you're going to solve these more complex equations, you will need to approximate them anyway, and you need to make sure that you're getting at least the diffusion right? Because if you do like anything and you cannot get the diffusion right, then your solution is meaningless. It's what we say, garbage in, garbage out. You don't know the accuracy of your numerical methods, then you cannot really trust what the computer is telling you, alright? So then let us start with let's start studying how we construct these approximation methods, and then I go to my notes here, and then we have like some very interesting. So we have that Gaussian that I showed there is the heat kernel, the k of xt, and like I said, we take the convolution of a signal with this kernel, and then we find the solution of the heat equation. And here we see that we have a very interesting condition that this kernel must satisfy. Alright, so if I go back to Krita, we go here. So if we have, here we have x, here we have t, and suppose we have here t1, and here t1 plus t2, alright? And here we have some signal, and at t1 we'll have another signal, maybe something like this, and at t1 plus t2, you have some, I don't know, maybe something more, even more spread out. Okay, so and then if I compute, I can understand the evolution of this thing in two ways. I can see that there is a kernel here for t1 and a kernel for t2. Alright? But I could also say that I am going directly here, and this will be the kernel for t1 plus t2. And how does this thing all consistent? So if I understand the evolution this way, I need to pick f of x and do the convolution with the kernel at t1 and then later with the kernel at t2. But if I go this route, I need to take the convolution of f of x with the kernel at t1 plus t2, and this must be the same thing. And it turns out that the convolution is an associative operation, so all that means is that the kernel at t1 plus t2 equals the kernel at t1 convolution with the kernel at t2, and that's all that this equation is saying, right? That the convolutions at different times, when you add, they must match. But we know from the last video that this kernel is actually a Gaussian, so let us study convolutions of Gaussian. So if I pick here a Gaussian where the variance is sigma squared, remember that we have the standard deviation, which is sigma, and the variance, which is the square of the standard deviation, which is, we denote sigma squared. Then if we take this normalized Gaussian, when we take the Fourier transform, we obtain another Gaussian, but now the variance is 1 divided by sigma squared. So you see that if I multiply the variance of the, well, in our conventions for the Fourier transform, this Gaussian is not normalized, but if we take the, if we multiply the variance of the Gaussian in real space with the Gaussian in frequency space, we get 1, right? And this is some sort of uncertainty principle associated with the Fourier transform. This is really the uncertainty principle in quantum mechanics, because in quantum mechanics, position and momentum are Fourier transforms of each other, and it means that if a signal is very localized in space, it is very spread in frequency space and vice versa, right? Okay, and then so if we want to calculate the convolution of two Gaussians, now we have the first Gaussian has the variance sigma 1 and the sigma 1 square, sorry, and the second has sigma 2 square. If we want to calculate the convolution, we simply multiply them on frequency space, then we're gonna have this. And then when we evaluate the inverse transform, we found something very interesting, that it's still a Gaussian, and the variance is now the sum of the variances of the previous one. So we have a very interesting property that kind of guarantees that this equation here is true. It's because the Gaussian is stable with respect to convolution, right? If you take the convolution of two Gaussians, the result will be another Gaussian with the variances are summed. And if you recall, yeah, this is just what I said here in form of an equation, and if you recall, the variance of a Gaussian when the solution of the heat equation is 2dt, right? And then so this statement that the kernel is the convolution at different times simply means that it's this equation sigma squared 2dt, but I can break up t1 in t1 plus t2, then I have 2dt1 plus 2dt2, and then the variances, they do add up, so that's the previous equation for the kernel works. Alright, cool. And then, in view of this, we can do the so-called time stepping method to approximate our solution, because we can define, we can essentially take the end convolution of a function, which is if, alright, so here's just the definition of it. So f1 is just f, and fn is that f is star fn minus 1, and this is the recursive definition of the fact that you are simply taking the kernel and convolving it with itself n times. And then when we if we divide the time interval into m equals, we just need to compute the kernel at a time step delta t and take the convolution m times, and we have our kernel. So if we go back to Krita, all that this is saying is that we can do, perhaps I can, without erasing all of this, all of this is saying is that I can do this, and then so suppose this is the t that I want to evaluate, right? So I can break this interval into several segments. Each one of these is delta t, and we have m of them, right? So if I know the kernel for delta t, so if I know what is the kernel for delta t, I can simply, each step of this is a convolution, and then I can simply take the convolution of this kernel with respect to itself m times, and then I will get the signal here, right? That's all that it's saying. And the most amazing thing is that we have this statement from probability theory called the central limit theorem, that if you take the convolution of any probability distribution, not only a Gaussian, for a larger number m, the limit of this sequence of convolutions will be a Gaussian, right? That's what the central limit theorem says. It's actually a very, very powerful result. And what it means for us is that we don't need to be exact. So if we approximate this kernel here, k of x delta t, as long as it has mean 0 and variance square root d 2d delta t, which is what we expect from our theoretical analysis, if I jump m steps for a large number of m, I should approach a Gaussian in that limit. So, as you can see, what this tells us is that the approximation for the kernel can be pretty much anything, but you must remember that calculating convolutions is expensive, right? So, when you do an approximation, for the approximation to make any sense at all, you need to be able to evaluate it fast, and to ideally also run in a small number of steps, because the larger the number of steps, the more computationally heavy your algorithm is. And ideally, since the FFT is ON log n, we would like to make this approximation in ON, and we'll see if that's possible. Yeah, we're actually just spoiling a little bit. It is possible. And then here I will present the first and the simplest ways to do this, which is the so-called explicit method to solve the heat equation. First, let's start with the finite differences method. Well, it is actually a very simple method, is that if you take the heat equation, which is del u del t equals d del square u del x square, what we do is we approximate this derivative by a difference of the field, right? So instead of the continuous derivative, we compute this equation for a finite difference. And the simplest way to approximate the derivative of a function is the Euler method. So here, if we write the second order Taylor series, we have f of x plus h equals f of x plus h f prime of x plus h squared divided by 2 f double prime of x. Of course, there are other terms, but I am omitting them. So here I can isolate f prime and say that, and when I divide it by h and isolate f prime, I have f prime of x equals fx plus h minus f of x divided by h plus OH. So you see that when we approximate it by this, the error is of order h. Right? Another way to approximate the derivative by differences is the so-called central differences method, or central difference approximation, where I write now the fourth order Taylor series. We have f of x plus h equals f of x plus h f prime of x plus h squared divided by 2 f double prime of x plus h cubed 3 factorial f3 of x plus h4 4 factorial f4 of x. And if I expand it in fx minus h, it's the same thing, but now the odd powers of h gain a minus sign, right? And if I subtract the second from the first, we have that f of x plus h minus fx minus h equals 2h f prime of x plus oh cubed. And then we have that f prime of x equals fx plus h minus fx minus h divided by 2h plus oh squared. And also, if we sum the first and the second, we get an approximation for the second derivative, which f double prime of x equals fx minus h minus 2 f of x plus fx plus h divided by h squared plus oh squared. And one very interesting thing that you should notice is that this approximation here, where I pick the number from the right and subtract one from the left and divide by 2h, this is more accurate than the Euler one, because here the error is oh squared, while here the error is only oh, right? So if you take h less than 1, for example, this one here will perform better. And our approximation for the second derivative is also oh squared. Alright, so with this in mind, now we can write the heat equation, and then I'll introduce the so-called forward time-centered space scheme, or FTCS. And what we're going to do is we will discretize the field, and then we introduce this U sub j super L, which is U evaluated j delta x L delta t. This L here does not mean to the power of L, it means just that it's evaluated at a time L delta t, right? And the idea in this FTCS scheme is that we write the time derivative in the Euler method and the space derivative using this central differences method, right? And if we do this, we have UJL plus 1 minus UJL divided by delta t equals d UJ minus 1L minus 2 UJL plus UJ minus 1L divided by delta x squared. And to just introduce some notation, if we let alpha equals d delta t divided by delta x squared, we can rewrite this as UJL plus 1 equals alpha UJ minus 1L plus 1 minus 2 alpha UJL plus alpha UJ plus 1L. And we also, together with the boundary conditions, if we set that U0 of L equals UN of L equals 0 for every L, then we can apply this relation to obtain, given the configuration at L equals 0, we can obtain it for L equals 1 and L equals 2 and whatever, right? So perhaps it's a good idea to draw this. Let us go back here to our board. so that if we have here 0, this is t, and this is x, and here is L, where we have the boundary conditions, and that is that all of these here are known because these points are known because of the boundary conditions, and then these are known as well. And these here at t equals 0 are also known because they are our initial field configuration. And the idea is that when we evaluate these here, that one was larger, wasn't it? So there's here and then here, okay. That is that when we evaluate this one, so the FTCS schema express these guys in function of this, this, and this, and similar this one in function of this, this, and this, and so on. And that's why we call this an explicit method, right? Because it provides these blue guys, the next ones, to be evaluated explicitly in terms of the values that are already known. Okay, cool. Now we'll see that this method has a very annoying problem, which is its stability. Okay, so remember when we discussed the Fourier transform that what we're doing is actually approximating a kernel, right? But this here, you see, this should only make sense if the Gaussian that corresponds to this time step, the width should be more or less of the order of, the standard deviation should be more or less of the order of delta x for this to make sense. Because if the time step is too large, then you have a very spread out Gaussian, and there is no reason why it should depend only on the points, only the nearest neighbors, right? And if you recall, the analysis that we did at the last video was that when this nearest neighbors approximation should be good, it's around delta t approximately delta x squared divided by 2d. And then if you substitute this, we have our converted alpha equals 1/2. And then you see already something odd here, because if you substitute alpha equals 1/2, what means this term will be 0, and then these two will be half and then half. And then you see that it looks weird, right? Because from this argument you would expect that this guy in the middle would have the greatest contribution, but in fact its contribution is 0, and all the contribution comes from the neighbors. It's just an average of the neighbors. So what is really happening is that this value is actually it is not when the method is good, it's like the border where it's stable. And to understand this, the rigorous way to do this is a so-called von Neumann stability analysis. And the reason it works is because when you discretize it, when you put an equation like this, right, you can kind of do a Fourier analysis just as you can in the continuous problem, but the evolution of the Fourier modes will be different than in the continuous one, right? And then what the von Neumann stability analysis does, it evaluates this evolution of the Fourier modes subject to this delta t discretization. And then so if we substitute the ansatz ujl a to the k l e to the power of ijk delta x, so here this is only like a Fourier mode, right? And then this AK is the amplitude of the Fourier mode, and this L, this really means to the power of L. Now it really means that. And the idea here is that if the absolute value of this AK is larger than 1, then the scheme is unstable, right? Because the Fourier modes, they are growing as we iterate the solution, and we know from the heat equation that they should decrease, right? And then if we substitute this, we have some kind of a mess, right? But we can clean this up by divided by AKL EIJ K delta X. And when we do this, we have AK equals 1 plus alpha e to the minus IK delta X minus 2 plus e to the IK delta X. And here we use the Euler identity, and then we replace this with 1 plus 2 alpha cosine K delta X minus 1. Great. But we saw in the first video that the maximum value of K delta X occurs at the Nyquist frequency. It is pi. So this, for our sampled signal, the maximum that this can have is pi. And the minimum is at the 0 mode K equals 0. So if we substitute K equals 0 here, what happens is cosine of 0 is 1. 1 minus 1 is 0. 1 plus 0 equals 1. So we know that the 0 mode is 1 and the border is stability, but it is right, because the 0 modes, they do not decay under the heat equation, right? However, when you have K delta X equals to pi, we have cosine of pi is minus 1, minus 1, minus 1, minus 2, and then we have AK equals 1 minus 4 alpha. And what happens is that if alpha is greater than half, we have that AK is less than minus 1, and when and then we have the absolute value of AK is greater than 1, and this makes the scheme unstable, right? So what we see here is that this value of alpha equals half is pretty much the largest value that makes this scheme practical, because if alpha is larger than 1/2, the high frequency modes will diverge. And usually, when for real signals, the very high frequency modes, they're not very important. They're usually like noise or some discontinuity, but they are there. And if your scheme handles these guys in a way that makes the solution blow up, it is not useful for anything. So because of this, when you use this FTCS method, the time step has to be very, very small. If you remember in our example that we did in the example that we did, you see here the yellow one where something starts to happen. Here this time is 0.002. So what would be this delta t in the FTCS scheme to achieve the same result? Well, we used n equals 100, so delta x would be 10 to the minus 2, right? 10 to the minus 2 square is 10 to the minus 4. D equals 1, so 10 to the minus 4 divided by 2, we have 5 times 10 to the minus 5. We have 0.00005 there. So to arrive at this, we did 40 time steps with the largest time step possible. So even for this initial step here, we need 40 iterations to converge. So you see that this method has some issues, right? But to illustrate them further, I did something I showed this in a graph, so let me see. So just to show what this code is doing, why I am actually plotting the frequency response, and I am plotting the exact one, which is the exponential of something times k squared, which is the correct one, and the one that we get from the FTCS scheme, which is 1 plus 2 alpha at cosine thing -1, and the code kind of knows the constants, right? And then, so if I put here the time 5, 10 to the -5 and plot, look at here, you see that the exact starts at 1 and decays like a Gaussian, right? And but in the FTCS one, it just starts at 1, decays much faster, and it's at -1 at the highest frequency, where it's in the border of stability, right? And this is like completely wrong, because as you see, these high frequencies here, they should be suppressed and not only preserved with a phase of pi, right? And you see that it is like killing the frequencies of the middle, which should not happen. So yeah, while if it is not really that big of a deal if you don't get those higher frequencies, right? But if you let them just like diverge the methods, you simply cannot apply it, right? But if I reduce the time step, so for example, if I put here 1, look at this, very interesting. You see, if I put 1, the FTCS now has a different behavior. It's like the response for the higher modes is higher than the exact one. Of course, when we do several time steps, it will eventually converge to the exact one. But you can see that sometimes there's some sort of optimal time step where it becomes very, very close to the exact one. By experimenting, I kind of figured out that for the parameters that I have for my problem, if I set the time to 2, you see the FTCS one and is there, is very close to the exact one. But for our problem, this time step of 0.00002, I would require 100 time steps to converge. Alright, and just a demonstration here. So here's what this code is doing. What I'm doing here, I'm plotting the initial field configuration and the FFT solution, which is the exact one. And then to plot the FTCS one, I do an iteration of, I run m times the convolution of y with alpha 1 minus 2 alpha alpha, and it's same. So what this does is it computes this sum here, right? It computes this sum m times. And then if you remember that the most I am running for t equals 0.002, which is that first curve that we saw in the other example. And then if you remember, the largest viable time step is 0.00005, which correspond to when we segment the interval by 40 times, right? So if we put this 40 here, what we get? See that it is in the border, but it converged pretty well, but you can still see some artifacts because of this discontinuity here. This is a very high mode frequency, and you can still see here that these high frequencies did not decay correctly because of that, right? And suppose I ignore this analysis that we did, I segment it in less, I use m equals 30, that I use a time interval larger than what stability analysis tell me to do. And when I do this, look at this, so just 200,000. So at that point where there was a discontinuity, the thing just diverged to the point that you can't even see the initial FTDs was. They are just too small compared, so the solution blew up, right? It is completely unusable, this solution. Alright, but if I go more than what the analysis tells me, if I divide it by 50 instead of 40, which was 1, then I will get, See, now I get the exact thing. So the green curve is exactly matched to the yellow one. So in the conclusion, we in this video introduced you to explicit methods to solve the heat equations, and as you saw, they can work, they are good, but they have this advantage that too large time steps make the scheme unstable, and for this reason you usually have to choose very small time steps for it to work, and for this reason they are not that computationally efficient. And then in the next video we'll show how we can bypass this limitation, which you will see is that when we use instead an implicit method, then this scheme is unconditionally stable and very good. We can use larger time steps. Well, that's it for now, and I see you in the next video.